Welcome to Selection with Sathi. Today we cover topological sort, a fundamental algorithm for ordering tasks with dependencies. We will learn two approaches, Kahn's BFS and DFS-based methods, with complete code walkthroughs and dry runs. This is a favorite topic in GATE CSE and coding interviews. Let us begin. First, what is a DAG? A directed acyclic graph. Directed means every edge has a specific direction. From U to V, acyclic means there is no way to start at any vertex and follow edges back to it. Look at the code on the left. This DAG has 6 nodes. Node 0 points to 1 and 2. Node 1 and 2 both point to 3. Node 3 points to 4 and 5, which have no outgoing edges. This is a valid DAG. No cycles anywhere. Topological sort is only defined for DAGs. If the graph has even one cycle, no valid topological ordering exists. Kahn's algorithm uses BFS with indegrees. Look at lines 4 through 7. First, compute the indegree of every vertex. Indegree is the number of incoming edges. Lines 8 through 11 enqueue all vertices with indegree 0. These have no prerequisites and can be processed first. Lines 13 through 19, in the main loop, dequeue a node, add it to the order, and for each neighbor, reduce its indegree by 1. If a neighbor's indegree becomes 0, enqueue it. Lines 20 and 21. If the final order has fewer than n nodes, a cycle exists. Time complexity is O of V plus E. The DFS approach is elegant. Look at lines 4 through 9. The DFS function visits a node, recursively explores all its unvisited neighbors, and then pushes the node onto a stack at line 9. This is the post order. A node is added only after all its descendants are added. Lines 10 through 12 run DFS from every unvisited node to handle disconnected components. Line 13 reverse the stack to get the topological order. Why reverse? Because in post order, the node with no dependencies gets pushed first. After reversal, nodes with no dependencies come first, which is the correct topological order. Same O of V plus E time complexity as Kahn's. Kahn's algorithm has a built-in cycle detection mechanism. If the graph has a cycle, the nodes in the cycle will never reach indegree 0. They keep pointing to each other, so they never get enqueued. Look at line 16. We count how many nodes are processed. If count is less than n, some nodes were never processed. Those unprocessed nodes form one or more cycles. An alternative is DFS coloring with white, gray, and black. If during DFS you visit a gray node, that is a back edge, meaning a cycle. For Kahn's method, the check is simple. Just compare the count with n at the end.
Let us trace Kahn's algorithm on our 6-node DAG. Edges 0 to 1, 0 to 2, 1 to 3, to 2, 3, 3 to 4, 3 to 5. Compute indegrees. Node 0 has 0, nodes 1 and 2 have 1 each, node 3 has 2 because both 1 and 2 point to it, nodes 4 and 5 have 1 each. Only node 0 has indegree 0. Enqueue 0. Process 0, add to order. Reduce indegree of 1 and 2. Both become 0. Enqueue both. Process 1, add to order. Reduce indegree of 3 from 2 to 1. Process 2. Add to order. Reduce in degree of 3 from 1 to 2000. Enq 3. Process 3. Add to order. Reduce in degree of 4 and 5 to 0. Enq both. Process 4 and 5. Final order 0, 1, 2, 3, 4, 5, all 6 processed. No cycle. Now the DFS approach on the same DAG. Start DFS from node 2000. Visit 0, explore neighbor 1. Visit 1, explore neighbor 3. Visit 3, explore neighbor 4. Visit 4, no neighbors. Push 4 to stack. Back to 3, explore neighbor 5. Visit 5, no neighbors. Push 5. Back to 3, all neighbors done. Push 3. Back to 1, all neighbors done. Push 1. Back to 0, explore neighbor 2. Visit 2, neighbor 3 is already visited. Push 2. Back to 0, all neighbors done. Push 0. Stack is now 4, 5, 3, 1, 2, 0. Reverse it 0, 2, 1, 3, 5, 4. This is a different order than Kahn's, but both are valid. In both, every node comes after all its prerequisites. A classic interview problem, course schedule. 6 courses with prerequisites. To take course 1, you need course 0. To take course 3, you need both 1 and 2. To take 4 and 5, you need course 3. Model this as a DAG, prerequisite A for course B means edge A to B. This gives the same graph, 0 to 1, 0 to 2, 1 to 3, to 2, 3, 3 to 4, 3 to 5. Run Kahn's algorithm. All 6 courses are processed, so yes, all courses can be completed. The topological order gives a valid sequence to take the courses. If there were a cycle, like course A requires B and B requires A, Kahn's would detect it and return none. Now let us see what happens with a cycle. Graph 0 to 1, 1 to 2, to 2, 0. Compute in degrees. Node 0 has in degree 1 from edge to 2, 0. Node 1 has in degree 1 from edge 0 to 1. Node 2 has in degree 1 from edge 1 to 2. Every node has in degree 1. No node has in degree 0. The queue starts empty. The main loop never executes. Count stays at 0. Check, count 0 is not equal to n, which is 3. Cycle detected. This makes intuitive sense. In a cycle, every node has at least one predecessor, so no node can be the starting point of a topological order.
Quick exam tips. First, topological sort is only defined for DAGs. If the graph has a cycle, no valid ordering exists. Second, multiple valid topological orders can exist for the same DAG. Kahn's and DFS may produce different orderings, and both are correct. Third, whenever you see a prerequisite or dependency problem, model it as a DAG and use topological sort. Fourth, in GATE, they often ask you to find a valid topological order from a given DAG or determine if one exists. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.